So we've got another Olympiad question here, and this is an algebra question from an older paper, I believe 2006, yeah. And a clarification I've got to make in the previous two ARMO problems, these are from the list of shortlisted problems, okay? So they're not necessarily problems that ended up on the actual exam. I think at least one of the two we covered in the last couple of videos was actually featured on the Olympiad exam, but yeah, a load of problems are shortlisted and they're picked by a committee, and I'll just pick out a couple that I think would be good to cover on the channel. So for this one, and I encourage you, if you want to have a go, just to pause it, read through the question. It's on screen now. I'll just get the cursor out of the way, and you can have a go at it yourself. We're going to get into the solution now. So we have a sequence of real numbers, A0, A1, A2, so on, and we define them recursively. So that A0 is equal to -1, so we define some initial term. And then we have that this sum from k equals 0 up to n of the a(n)th minus k term, or n minus kth term, over k plus 1 is equal to 0 for whatever n is. Okay, so we use that to define a1, and then now we have the value of a1, we can use that to define the value of a2, and so on. And our job is to show that an is a positive, all the an's are positive for n greater than or equal to 1. So essentially, apart from this term we're given, every other term is positive, so that's our job. When we're looking to prove that something works for all n greater than or equal to 1, and we're looking at, obviously because we're looking at terms in a sequence, we're looking at whole numbers here, induction is very much on the card, so we're going to look to use that, and we'll start with the anchor step now. Okay, so for the case when n's equal to 1, we know that the sum from k equals 0 up to 1 of an minus k over k plus 1 is equal to 0, but this is also equal to a1 plus a0 over 2, and like I say, that's equal to 0. And this is -1, so that clearly gives a1 equal to 1/2, and that's greater than 0. Okay, so this result we're looking to prove is true when n is equal to 1. For our induction step, we're going to assume, as always, that for some n greater than or equal to 1, we're going to assume that a1 up to an is greater than 0, so all those terms are greater than 0, and then we're going to rewrite the recursion formula in a way that's more convenient to us. So, and write the recurrence formula. I'm not sure about my spelling here, you'll have to correct me on that in the comments. Rewrite the recurrence formula for n and for n plus 1. The reason we do this is because we're assuming that all these terms are positive for n, and then we're going to write out the condition that we must have to define the a(n)th plus 1 term, and we're going to try use this and a relationship between them, use our assumption to prove that therefore must be true that a(n plus 1, as in the a(n)th plus 1 term, is positive. Bit of a mouthful. Anyway, so the way we do that, and this is respectively, so we're writing the one for n first. So k up to 0 of n of ak n minus k plus 1 is equal to 0. And take a moment to convince yourself that that's the same as the relationship we were given before. And for n plus 1, we get k equals 0 n plus 1 ak over n minus k plus 2, and that's obvious because we've just substituted in n for n plus 1, so we get this plus 2 here, and that's equal to 0. So then we perform a particular subtraction because of our assumption that this is, all these terms are positive. no, sorry, not because of that assumption. Because these are both equal to 0, when we subtract any linear combination of them, it's equal to 0, and the linear combination we actually choose is we say 0 is equal to n plus 2 multiplied by k equals 0 up to n of up to n plus 1, sorry, of ak over n minus k plus 2, and then minus n plus 1 k equals 0 to n ak over nk n minus k plus 1. So that's all equals to 0. Why do we multiply this by n plus 2 and this by n plus 1, you might ask? Well, when we combine these terms later, you're going to see that the sort of cross multiplication here, by having this n plus 2 and n plus 1 term, we get a convenient cancellation later on. So we're going to write that out slightly more concisely. So here we get n plus 2 multiplied by an plus 1, okay, because what we want to do is write these both as sums from k equals 0 up to n, so we can combine them. So we just take out the an plus 1th term, okay, because we can do that. This is just the sum, so instead of now this being a sum from k equals 0 to n plus 1, it's a sum from k equals 0 to n plus the extra term. We just add that on separately, and then we get plus the sum from k equals 0 to n of, and this is where we combine these two sums, n minus k plus 2 minus n plus 1 over n minus k plus 1. That's all multiplied by ak. Okay, so that looks alright. Note that the a0 coefficient vanishes. Yeah, the a0 coefficient vanishes because plugging k equals 0 in gives n plus 2 over n plus 2 1 minus n plus 1 over n plus 1, which is 1, so that just disappears. So now rearranging, we get that an plus 1 is equal to 1 over n plus 2, the sum from k equals 1 to n of n plus 1, n minus k plus 1 minus n plus 2 over n minus k plus 2, all multiplied by ak. Okay, and combining these two terms now, we're almost there. It gives us k over n minus k plus 1, n minus k plus 2, all multiplied by ak. So by our assumption, all these ak's are greater than 0. Okay, so that was our assumption. K is obviously greater than 0. We're summing from k equals 1 up to n, and the minimum value, the maximum value we're taking off here on the denominators is n, so that would still give us 1 times 2 on the bottom, which is obviously positive. So all of this is positive, so if the first n terms are positive, the n plus 1th term must be positive too, and that completes our proof by induction because we have that anchor step that a1 is positive. So that's a nice proof by induction. Hopefully you enjoyed that. I thought it was quite a nice problem. If you've got any particular problems you've seen on the shortlist that you're working through that you want covered on this channel, you want the solution talked through, like always, this is the solution given in the problem. If you want that list of problems, I can leave them linked in the description. In fact, I will do that, so you can see where I find these problems, and you can go through a few for yourself. Yeah, if you have any questions about this solution or bits I missed out where I skip through a bit too quick or whatever, let me know, or any other feedback about the videos would be much appreciated. So thank you very much for watching, and I hope to see you in the next one.